Now let's get some practice using trig identities to simplify expressions that involve trig functions. For instance, this one. Notice that this looks like a pretty messy expression, and if I wanted to use it, for instance, to find values or some other thing, there's a lot of pieces I need to plug x into here. However, if I can get this down to like one fraction or one term, then I will have a lot less I have to do. So since I have cotangent, tangent, cosecant, and secant, I know all of those have identities telling us how to write them in terms of sine and cosine. So let's do that, just so we start with everything on the same page. Maybe that'll give us an idea where to go. So cotangent is 1 over tangent of x, or the other identity we know is that it's cosine x over sine x. Tangent x is sine x over cosine x. And then cosecant is 1 over sine x. Secant is 1 over cosine x. Now I want to look at this and see if I can simplify it more. Well, first of all, when I multiply two fractions, I just end up with one fraction. So I get 1 times 1 over sine x times cosine x. And I notice that I have sine, cosine, and sine times cosine for my three denominators. So if I get a common denominator, I can add these three fractions and just get 1. So here I'm missing a cosine x in my denominator, so I need to multiply by cosine x over cosine x. Here I'm missing a sine in my denominator, so I need to multiply by sine x over sine x. And then the last term already has both, so I can just leave it alone. Okay. Well, let's see if I can simplify. First of all, we do have a common denominator now, so I can add these three fractions together. Also, cosine x times cosine x and sine x times sine x can both be simplified and written as squares. So I get cosine squared of x plus sine squared of x plus 1 in the numerator all over sine x times cosine x in the denominator. Now I have some squares in there, so I might want to look at my Pythagorean identities and think about if there's one that helps. Well, I notice I have a sine squared. I also have a cosine squared. Well, if I add those two, which I am over there, then I get 1. So if I add cosine squared x plus sine squared x, I just get 1, add it to the 1. So I get 2 over sine x times cosine x. Again, if I were to try and find values from this expression or something, I'd much rather work with this than I would that. Okay, let's look at the second one. This one, I notice that I have these two things being multiplied first. And I have a secant squared. So I could go through and change everything to sines and cosines, but I think I want to multiply this out first and see where it gets me. So I have 1 times 1 gives me 1. I have plus tangent x minus tangent x, so those will cancel. Then I get minus tangent squared x from these two terms when I multiply. Then I have a plus secant squared x. Now, there are a couple different ways I could proceed from here. As I said, I could have started by changing everything to sine and cosine, and then I have some fractions to get common denominators with. If I do proceed this way, then I see I have a secant squared of x, and I also have a tangent squared of x. So I'm thinking I want to use this Pythagorean identity in some way. I notice that I have a secant squared of x, so why don't I just take this piece and put it in for secant squared. So instead of secant, I want tangent squared plus 1, should be an x. Let's see what happens. So these guys are going to cancel and become 0. So I have minus tangent squared x plus tangent squared x. Then I have 1 plus 1. Well, that's 2. So that means that this whole expression, no matter what x I put in, is just going to be equal to 2. Another way I could have done this, I could have come back to this step, and if I notice, if I look at this expression, or this equation, this identity, if I move the tangent to the other side by subtracting it from both sides, I end up with 1 equals secant squared of theta minus tangent squared of theta. Well, if I do a little bit more manipulation here, as long as I leave the negative with the tangent, I can switch the order, and I end up with exactly this in this expression, which tells me that this is equal to 1 plus 1 or 2. So as you see, there are multiple ways that you could have done this. Depends on which way you recognize the formula or the identity. Again, you could have also started with sine and cosine. You could have had sine x over cosine x, sine x over cosine x, and 1 over cosine x squared. We would have had sine squared x over cosine squared x here, 1 over cosine squared x here. We would have just found a common denominator and we could subtract across. And we probably would have ended up using this identity somewhere along the way. Okay, let's look at one more of these before we try something a little different. So I want to take tangent of theta, and I want to multiply that by 1 over 1 minus cosine of theta minus 1 over 1 plus cosine of theta. Okay. So first of all, I notice that all I have over here are cosines. Here I have a tangent. So just so I have all cosines and sines, let's switch that to sine theta over cosine theta. Now, I notice that I have two fractions here. I could either distribute this across, or I could try and combine these two inside first. Either way, this would work, but I think because I see these will give me a nice denominator when I multiply them, I actually want to combine inside first. So my denominator is going to be 1 minus cosine theta times 1 plus cosine theta. So here I'm missing the 1 plus cosine theta. And here I'm missing the 1 minus cosine theta. Okay, so now I can subtract right across the top, right? So I get 1 plus cosine theta minus 1 minus cosine theta. Well, if I distribute this negative across, I get minus 1 plus cosine theta. Because the negative distributes to the 1, it also distributes to the cosine. And then, for my denominator, I can actually multiply those pretty easily, because that's going to give us a difference of 2 squares. So I get 1 minus cosine squared of theta. So on top, I'm going to get 1 minus 1 plus cosine theta plus cosine theta, so plus 2 cosine theta. And then on the bottom, I don't necessarily want 2 terms there. I have 1 minus cosine squared of theta. If I could write that as 1 term, it'd make me much happier. So I have a cosine squared. Let's look at this identity for just a second. So if I know what this is equal to, if I move the sign to the other side, I'll get something that's equal to this. Well, if I want to know what sine squared is equal to, I can move the cosine to the other side, and I'll have sine squared equals, and it happens to be that when I do that, I get sine squared theta equals 1 minus cosine squared of theta. So I can always manipulate these identities if I want to. So if I move the cosine to the other side, I get sine squared theta equals 1 minus cosine squared theta. Well, I have 1 minus cosine squared theta, so we just figured out that that's equal to sine squared theta. Now maybe that wouldn't always help, but in this case, notice that it does, because I have a cosine on top and a cosine on the bottom, and I have a sine on top and 2 factors of sine on the bottom. So one of those will cancel, so what I'm left with is 2 over sine of theta, which is much, much simpler than what we started with. Okay, let's try something a little bit different now. So far we've just been given an expression and we just want to get it as simple as we can. What we're going to try now is I actually want to verify some equations. So we're going to start with this. So we have cosine x minus sine x times cosine x plus sine x. And what I want to do is I want to make sure that this is actually equal to what I'm claiming it's equal to. I'm claiming that's equal to 1 minus 2 times sine squared of theta, or x. I'm mixing my thetas and my x's. There we go. So I want to manipulate either one side or the other and see if I can get them to be equal. So I noticed that this one has a sine squared, so I could do the same thing I did before and move the cosine squared and use 1 minus cosine squared. I'm not convinced that that's really going to help me though. This side already looks pretty simplified. So let's go ahead and multiply this side out, see where we can get. So I have cosine x times cosine x, so that's cosine squared of x. Cosine x times sine x minus sine x times cosine x. So those guys are going to cancel. Our middle two terms will cancel. And we have minus sine x times plus sine x. So again, we have a difference of 2 squares here. And we want to know, is that equal to 1 minus 2 times sine squared of, not theta, of x. Now, notice that this side, I'm not going to do anything to it, I'm not going to touch it, but this side has a sine squared in it. I have one sine squared over here, but I also have a cosine squared. So what would be nice if I could somehow take that cosine squared and make it into a sine squared using one of our Pythagorean identities, probably, since we're dealing with a square here. Maybe what I can do is I can find an equation using this one for cosine that will give it to me in terms of sine. So just like I did before where I solved for sine squared for this piece here, I can move the sine squared to the other side, and I'm going to get that cosine squared of theta is equal to 1 minus sine squared of theta. Just by moving this to the other side. So if I use that instead of cosine squared of theta, or of x I should say, it's pretty easy now to see. I can combine my like terms. And we do indeed get the equality we were looking for. Those two things are going to be exactly the same. So what did I do? I actually left this side alone the whole time. I manipulated this side and ended up getting the same thing. Let's try this one. This is going to be the same type of deal. I'm going to give you an equality, and we want to make sure that it indeed is true. So I'll put a question mark because we're trying to double check that. So even more so than this example where we said this side was pretty simple already, this side is about as simple as we can make it. We could change it to sine x over cosine x, but that's about all we could ever do to this side. So let's start by working on this side. And the only thing that's really immediately obvious, I think, is to change the tangent on that side to sine x over cosine x. And then, the only thing I really still see to do is to get a common denominator and add these two fractions. Or these, well, this one's not even really a fraction. So if I multiply this side by cosine over cosine, I'll get my common denominator and I can add the numerators. So I multiplied by cosine x over cosine x times that first term, we get a common denominator, we can just add right across the top. So that's just the numerator, and we have our denominator. Okay. So I noticed that there's a sign in the top of both of those two terms. So let's try pulling that out, see if that gets us anywhere. So now at least I'm seeing that I have a matching term. So maybe this will somehow help me. But I have a fraction being divided by another fraction. So what I can do is I can take the reciprocal of the bottom fraction and multiply it times the top fraction. So we get sine x cosine x plus 1 over cosine is times 1 over cosine x plus 1. So we have a matching factor on top and bottom. So what we're left with is sine x over cosine of x, which is indeed tangent of x, which is what we wanted. So we verified that this is true. So notice that one, and even the first example I did, I really only worked on one side and I made it look like the other side. In an example like this one, secant squared x plus cosecant squared x is equal to secant squared x times cosecant squared x. We may need to work on both sides. So notice that this looks like a pretty unusual one. So we want to make sure that that's true. I'm not really comfortable working with secant and cosecant, at least not as comfortable as I would be with sine and cosine. So let's switch them right to sine and cosine. Notice that secant of x is the same as 1 over cosine of x, and then I'm squaring that, but to square that I square the 1 and I square the cosine. So it ends up being that. The same thing will happen here. I'll get 1 over sine squared of x. And I'm just going to work on this first side for now, just so I don't get confused as to what I'm doing to which side. Because I don't want to actually change it, I'm just manipulating it. So I have two fractions. I probably want to add them together to get one fraction. So my denominator will be sine squared times cosine squared. Here I'm missing the sine squared, so I need to multiply by that on top and bottom. Here I'm missing cosine squared, so I need to multiply by that on top and bottom again. So what I end up with is sine squared of x plus cosine squared of x, which should look familiar to us, over sine x times sine squared x times cosine squared x. Well, sine squared plus cosine squared is one of our Pythagorean identities. That's just equal to 1. So I get 1 over sine squared x cosine squared x. Now it's not immediately obvious to me how to get between these two. I could probably do it, probably wouldn't take me that long, but I kind of want to work on this and get this into all sines and cosines. See if I can make these look the same. So on this side, I'm going to work again. So I'm going to use the same trick I used here. Secant squared is 1 over cosine squared of x. And I'm multiplying by 1 over sine squared of x. Well, when I multiply those fractions, I'm going to get 1 over, I'm going to flip the factors around. It doesn't matter. 1 over sine squared x times cosine of squared of x. Well, these two are the same thing. So that means we verified it. If we can get both sides by working on them independently to look the same, then we have verified the equation.